Okay, so without further ado, thank you everyone very, very much for coming. I'm honored to be coming in today from the traditional and ancestral territories of the Coast Salish peoples. Today, we are wrapping up our winter colloquium series with a very special guest, Laurie Rousseau-Nepton from CFHT, who's going to be telling us about the awesome Signals project, a survey of star-forming regions in the local universe. So take it away, Laurie.
Thank you, and thanks for inviting me. I'm starting my day here in Hawaii at 9 o'clock. I have my coffee. I'm in my office in Waimea, and I will talk about signals. But before I get there, I know some of you in the audience are students, and I wanted to introduce a couple of things, what led to signals, and also talk a little bit about the instrument CITEL, which I'm the instrument scientist of, so that you guys know what it is and maybe get interested in using it, of course. And as an astronomer or resident astronomer at CFHT, my job is to help people to use the telescope, not only CITEL, but all the instruments. So if ever you have any questions after the talk or any inquiry about any of the instruments, you can email me. I'll be happy to help you with that. But today we're going to focus on signal and how I got there. And I like to start from Canada because this is a picture of Mont Mégantic. I was, well, actually, I'm right here on the picture. And I was a senior student at that point. And part of my project as a student was to test Espion, which was the predecessor of CITEL. And Espion was a prototype instrument. And as part of the team, I tested it. I was also in charge of checking if we could do science with it. It was like the first student project that could actually use data from it and efficiently do science. So I worked a bit on data reduction, data analysis, procedure at the telescope on how to calibrate the instrument. And I still do kind of a little bit of that today with CITEL. And I also trained students to use the telescope, and I was doing it back then. These students were there to learn about Espion, and sometimes I get students here for internship to learn a bit more about how we observe here at CFHT. So if you are interested in that, you can also email me. And my project was on Espion, the spectrometer, the Mont Mégantic Observatory. I was under supervision of Carmel Robert, who some of you, of course, know very well, and Laurent Drissen, who was the PI of the instrument, was also close to my project in a sense. So I was working with his team of students who were like part engineer and part scientists. And we together made it work. And also it led to CITEL eventually. So we could prove that Espion, the prototype, was working, and we got funding to build CITEL. And fast forwarding into time, we got CITEL in good shape for the first light in 2015. And we left Canada with a team to test the instrument. You will probably recognize me in the corner there. I was looking at the first data getting into the telescope. But at the same time, we had very poor weather forecast. There was this hurricane Guillermo that was going to hit the island. And at the very last moment, Guillermo decided to go north, and we had actually 7 perfect nights of observing, and I was a happy astronomer. And the first object that we actually observed was a planetary nebula that you might recognize on this picture here. But I was studying galaxies. My project with Espion was on galaxies, and I'm still doing that. I have been trained to study star formation in galaxies from the beginning. I love doing that. And it's also one of the reasons why I built the project Signal later on. I built up on my strength on studying emission line in galaxies and study star formation. And this galaxy was in the background, actually, of the picture. And I analyzed it very quickly to get some information about dynamic and content of the galaxy, chemical content of the gas around the star forming region. And so it was a very successful run. And it started my journey here because a little bit after that, I got hired to be a resident astronomer at CFHT. And as well, the first 2 years, I was also leading a postdoc position at the Hilo University. So I was working with Pierre Martin a couple of days a week and be at the telescope for the rest of the time to help with the operation. And these first year were critical in building the project. And so for those of you who don't know about Hawaii, this is the island of Hawaii, the largest island of the archipelago. And if some of you might know, there's active volcanoes on the island. They are actually currently active. The Kilauea is erupting. There's lava in the lake, in the crater, basically. This is a picture from late September, but I checked yesterday and it looks still the same. So we have to manage geological activity, earthquakes, vibrations, and also gases emitted by the volcano. So we have a bunch of sensors actually at CFHT to make sure that everything is protected from that. I could go a long time in explaining why the volcano gas are bad for our mirror or how the earthquakes affect Seattle, but it's just to give you a glimpse at it. And this is an old picture, but it actually looks a little bit like that right now. So this is the Mauna Kea. It's the largest volcano on the island of Hawaii. This is where I am privileged to observe. And the Canada-France-Hawaii telescope is right there on the left. And the Mauna Kea is also a sacred site for the Native Hawaiian. More recently, we have developed programs to teach a little bit more about the astronomers on what the Mauna Kea represents for the local community and how you need to take this journey to the mountain with in mind, you know, this interaction that it has with the community. And again, this is something that I'm probably going to be talking about to you guys on another presentation in a couple of months. So you'll hear about it on the Cascade Exploder at some point. We're preparing a little webinar on these topics. So yeah, stay tuned for that. But yeah, what I like about this image is that we see the mountain, we see also the clouds that are below. So most of the time when you drive up to the Mauna Kea, you can feel it's a very special place because you're often going through the layer of cloud and you reach the summit, who has more or less about 75% of clear weather through the year, which is exceptional. And on top of that, you are on a very tall mountain. It's more than 4 kilometers high. It's in the middle of the Pacific Ocean. So the image quality that you get on the Mauna Kea is typically very good, and even more at the CFHT site, who is one of the best sites on the mountain. So we don't have adaptive optic on CFHT. We used to have it in the past, but not currently. But still, we reach often image quality of 0.5, 0.6 arcsecond, averaging at around 0.8. So it's pretty good. So depending on your science, it could be very relevant. And now we're just gonna jump in to the building. This is the telescope, just to give you an idea of the scale. It's a 3.6 meter wide telescope. And we have prime focus instruments that are located on the top, and also Casgrain instrument, the spectrograph, and CITEL that goes below the telescope. And now let's just jump a little bit on a little introduction on star formation. For those of you who might not be studying that at all, and I like to start with a simulation. I'm a very visual person. You're gonna notice there's a lot of images in my talks, but this video is from my Tubate. It's from the UK Astrophysical Institute, and I love it because it's just the evolution of interstellar cloud with, of course, the ingredients that you need for them to evolve like this: little perturbation, gravity, and feedback from radiation. And you see the first stars emerging from the dense filaments. And in a cloud like this, in galaxies, you find sometimes groups that form like 10 stars at a time, maybe hundreds, thousands, 10,000, up to 100,000 stars in a cloud like this. So the scale can vary quite a bit. But these stars are sisters. They were formed inside the same gas. They have the same initial chemical composition. And this whole process is fairly quick. It is believed to occur within the range of 1 to 4 million years. And of course, it's almost instantaneous to, for the stars in there. And in some cases, it's a little bit, more efficient, or it happens on larger clouds, and you can form regions that have different characteristics. I like to just show like the Rosette Nebula, who has like, of course, like hundreds of stars in there and a couple of massive ones. And on the other extreme side, like the Tarantula, who has like some of the most massive stars known in the universe. And of course, many more stars. And also the isolated situation of the Rosetta, where you have like this perfect like spherical bubble, whereas sometimes it can be very complex, and all the different star forming region can be interconnected, which makes the analysis a little bit more complex, but also very interesting. And so inside of that lies, of course, the concept of the stellar initial mass function. So when the stars are forming, they are following what we know as the initial mass function of stars. So of course, there's only a few massive stars and a lot of low mass star. And they follow this function depending on where they are. But the question is, and a lot of people have tried to answer that question by studying different clusters of star, especially massive cluster of star, because they are populating the initial mass function correctly. If you don't have enough star in a star forming region, what you have is a very stochastic sampling of the initial mass function. Whereas if you have 10,000 stars or 10,000 solar mass inside the cluster, you have so many stars that they populate this initial mass function very well. And then you can start to correctly sample this stellar initial mass function. And one thing that is very interesting about star forming region that I study, the one that I am interested in, are the ones that still contain massive star, OB stars, the one that shine a very, very strong amount of UV photons, high energy photons that ionize the gas surrounding them. And the initial mass function is very well known in the range of mass around the solar mass. But when you want to know what is the initial mass function of the massive star, it becomes a little less precise because you don't necessarily observe them as often. And since they die off very quickly, you are also affected by the age of the region very much. And so there's a trick there that prevents us to have a very good grasp of the stellar initial mass function of the massive star. That's one thing that I'm going to come back to very late in my presentation. But on top of that, and I want you to keep in mind, I love this this graph here provided by Jennifer Johnson. Probably have seen it before, but just to draw your attention on this periodic table of the elements, where they're coming from. And of course, the massive stars are also responsible for a lot of the elements that are produced in our surrounding, but also elsewhere in galaxies. And some of the elements that we have access to when we measure emission line with instruments like CITEL are often, of course, hydrogen and helium, which are kind of our reference elements because they are produced by the Big Bang fusion. But then we also have access to nitrogen, oxygen, sulfur, and these elements are, as you can see here, produced and in different ratio by different physical processes. And oxygen is very well tied up to the exploding massive stars. And nitrogen is a little bit more tied up to the low mass star with a little bit of the massive star. And then sulfur is also a slightly different mix of the white dwarf and the massive star, which is interesting. So keep that in mind. And so what happened when we have those massive star, I was talking about the emission lines. So depending on what kind of star you have in a star forming region, this is a simulation that showed the ionization around the star of about a B type star. It happens very quickly, and this is for an O star, so more massive. It's happened just as quickly, but the bubble of ionized plasma around the star will be larger. Also the what we call the ionizing front, so the medium in between the ionized bubble and the neutral medium will also have different properties. And of course, we can compare that with observation when you're looking at object in the Milky Way, but very quickly, when you're looking further away, you lose that information. And studying star formation, to study it in really deep details, to really gather information and deep understanding of this process, you need a lot of information about what is going on inside the region. So of course you need the content, the stars inside, to kind of have an idea of the amount of photons that are emitted by those stars. This is going to interact with, of course, the interstellar medium around. So then you have the properties of the interstellar medium around that are really important. So I'm talking about the density of the gas, the abundances in the gas, and also the free electrons. And so for those of you who are not ISM, just quickly, what is going on in this gas is that you have those ionizing photons that are going to kick out some electrons off of stars, some atoms. Depending on the atoms, they have different energy. The electrons are not bound with the same energy. So you will have, for instance, of course, the hydrogen who needs 13.6 electron volt to get ionized, who will be fully ionized in a very large section of the nebulae. But if you go to larger, heavier atoms, I'm just going to pick one, for instance, like oxygen. The first level is the same as hydrogen, is 13.6 electron volt. But then if you want to go to the second level, it's 30 electron volt, or even like more than 50 electron volt to get to the third level. So you'll have a very different proportion of the different ions of the atom. And so that's one thing. And each of the elements have their own characteristics. But then you have all those free electrons that are bouncing around within a gas that have a certain density and a certain abundance. And these electrons have a certain energy, which is also related to the amount of energy of the photons that were there. And so this kind of super free electron is interacting with the gas, and it collides, like those electrons collide with ions constantly. And this process also is responsible of the emission of what we call collision line. So collision lines are produced very efficiently in nebulae like this because they only need a few electron volt in energy. So an electron can collide with an atom. What it will do to this ion, actually, it will slightly perturbate the electrons of the upper layer. It will give them a little energy, and often enough to put them in an unstable state. They would be like kicked off of their normal state. It will remain into that level of ionization, but the electrons are just moving a little bit. And very quickly, they come back to their normal state, and that's when they emit that photon at the very same color or wavelength that we measure with CETEL. So those are these very strong collision line, emission line that we measure. And of course, you also have the recombination line, which are related to when the electron is recaptured by an atom completely. And they are mostly observed in hydrogen and helium, very, very the amount of flux that you get in a line of recombination with heavier atoms are really small, because this is highly linked to the abundances of them in the gas. And of course, there's so much more hydrogen than there is heavier atoms. So basically, that's the physics going on here. And this is, we have different tools that we use to analyze this physics. And to get to the stage where we have this ionizing bubble, it goes very quickly. And then the massive star's life is of the range of 1 million years to 40 million years. And so we can observe these for quite a bit of time before they die off. But it's still very instantaneous in the story of a galaxy. Oh, and I like to put, Hawaiian picture of things. So like, this is the same physics as what's going on in like neon light, or of course the continuum of the stars is like all the colors of the rainbow. But this is really like the key elements here, and it is the key element in the science in signal. So in a galaxy like the Milky Way or typical spiral galaxy, this processes constantly happen in a lot of places. And you see these red bubbles, these bubbles of plasma are getting created around massive star, and they just appear and disappear very quickly. And while the massive star enriched the medium with stellar wind, and also ultimately by exploding at the end of their lives, they spread new ingredients into the gas, and they do that very efficiently. So studying massive star, where they are, their mass, why do they form the way they form, where they form, and in conjunction with studying the chemical abundances in the gas of galaxy and how this gas is mixed and the time scale of the mixing is the key to really fully understand the mechanism of evolution of galaxy chemical composition. And just to give you a other basis on the size of things, I like to just quickly show here. So you have an image here of Orion. Everybody knows this image is an HST image. Orion is a 4 parsec size H2 region. If you look at this galaxy now, 6822, you might notice this wonderful perfect bubble here, which is about 25 bigger than Orion. And then you can find H2 regions in that small galaxy of different size. And this actually region right here is a supernova remnant, which has like little clumps of about 2 parsec in size. So this is the size of star formation in those galaxies. But if you look further and wider range of galaxies, you might also find very large complexes of star forming regions, which might reach about kiloparsec in size. You have one here. And if you remember that 100 parsec perfect bubble that I just showed you, it would look very different at that distance. This would be the equivalent in size of about 100 parsec H2 region. And for a I want to say very far galaxy, but if you're studying the cosmology and galaxies at a redshift of 2 or 3, you might think this is a very local one, but for signals, this is the edge of what we study. So for this galaxy at 9 megaparsec, you have this 1 kiloparsec region, which is not very well resolved as much as when you're looking closer. And if we look in details in some region of this galaxy and we look at how we can detect the H2 region, and this is this image shows an output of our detection procedure, which basically detect peaks into the H2 region's emission, not only in H alpha, but also using other lines. And then it also creates contours. So the white lines, you see those contours are actually built up by trying to measure when a pixel is associated or closer to a peak, depending on the flux and its distance. There's also, we also included effect of the seeing or the image quality into this estimate, but basically it associated each pixel to one source of emission or one H2 region. And then within these that have been identified, if we zoom in again, just to look a little bit more in detail, you would have this region now, who is a few pixels in size. That would be the reference for 100 parsec region. And at the distance of this galaxy, that 100 parsec region would be actually very small. So it's a few pixels. And Orion, you might think would look like this, but it's actually even smaller than this. So this is the look, and I barely can see it on my screen. I hope you can still see it. But this little blue dot here is the size of the 100 parsec region. And this Orion region would not be detected at all. It's just, it's beyond your limit of detection. So going from there, that's why I'm studying the local universe with signal. If I go beyond that, we start to gather things that are mixed together. We cannot separate H2 region individually, and you cannot really study their physics. And H2 region are, of course, within the context of galaxies, included in an environment. Of course, that includes stellar population, dust, and also what we call the diffuse ionized gas. You can see those filaments here that are very faint. It's a little bit everywhere. It emits the same kind of emission line as H2 region, but in different ratios, and because it's the different physics in there. So you need to include all of these when you study farther away galaxies. And on top of that, the interstellar medium is very complex, and it has different phases with different temperature, with different level of ionization and densities, and contains a bunch of different atoms and sometimes molecules of different level of ionization, which kind of trigger probably a lot of biases when we study them and we try to really like extract the physics from them. And apart from these very various stage of the ISM, we also have a distribution of the source of ionization, those massive stars. They can be B star up to O star with higher effective temperature, and they can be located in different areas of the H2 region. And this is also something that if you don't resolve well, the region, you might get caught in the carpet. I don't know if it's a good expression in English, but I like this one in French. I'm just going to translate it like that. So you just get caught in the carpet, and it's not really going to tell you much if you don't see those effects, especially. So that said, then you have the line of sight from where you observe this that goes through this and that change. Anyway, so from there, you probably have all in mind now the kind of observation that we have and why CITEL is so important to study these H2 region in the local universe. So CITEL, for those of you who knows, you're probably totally agreeing with me. But if you don't know CITEL, CITEL is a spectroimager, just like Espion. It's a Fourier transform spectrograph. So we have a super large field of view of 11 by 11 arc minute. If you're doing imaging, you might think it's a small field of view, but if you're doing spectroscopy, you might think this is the greatest field of view I've ever seen. And that's true. CITEL is one of the largest spectroscopically covered field of view you can have on the planet. And so we can use it. And it gives you a lot of information, and more than 4 million spectra can be extracted from a data cube produced by CITEL. So how it works, it's because there's an interferometer inside. You might have been familiar with the typical Michelson interferometer. Just quickly from this like small video, you'll see like you have a source, can be the light coming from a galaxy. It enters the instrument, it hits a beam splitter, split the light in two components. There's a fixed mirror on one side, a moving mirror on the other. And by moving this mirror, you can change the phase of the beam who will recombine at the beam splitter. And this is what you detect. You detect interference pattern from this source as you move the mirror. So you move the mirror multiple times in order to build up what we call this interferogram here. And that's what the raw data of CITEL are like. And this is a simulation of different different source. So if you're not used to see interferograms, I can tell you that the amount of beatings that you see in an interferogram is basically the amount of lines that are responsible for this interferogram. So if you have 2 lines, you'll see 2 beatings. If you have 3 lines, you'll see 3, and so on. So I got really good at detecting lines just by looking at those interferogram from the raw data. But it's beautiful. And when you see those interferogram, you know that the instrument's capacity of making the light interfere was very well obtained. And that's critical for CITEL to have a stability of the mirror, stability in the instrument to make the light interfere. And we call this ability modulation efficiency of the instrument. So we want the instrument to be able to modulate the light from the 2 channel. And this is an example of raw data from the first object that we had observed. So you have the interferogram. There's this line here where we call the ZPD when the 2 mirrors are at the same distance from the beam splitter. You have the maximum amount of light. You can see it a little bit here. And then you have the air mass as the object moves. You need to correct for that. And so, so that's just a typical observation. And this was just 1 pixel. So each pixels of a data cube is like this. And of course, when you have a typical Michelson, half of the light would also go back to space. So CITEL is not a typical Michelson, it's tilted. We have 2 detectors to gather 100% of the light, so we can correct partially for air mass effect and absorption from clouds to a certain level. And also we can detect when there's like an external source of light that comes into play, like the moon's rising, for instance, and things like that. Which is very important. And because of that, what we see is not the bullseye, but a little bit on the side of the interference pattern. So it looks like this. And so if you shine a green laser into CITEL, this is the kind of data you're going to get. And if I made actually two short videos of a green laser inside the instrument, when you're close to what we call the zero path difference, the ZPD, you have one camera that sees constructive interference, the others see destructive, and so the flux come from one side to the other, and you see these very large fringes. And when you're very far away, so the mirror has moved quite a bit, then you see a lot of fringes. And believe me, if there's one bright fringe on one detector, the other detector at the bottom see the inverse. So energy is conserved. The physicist is happy. And now if we look at one pixel and we want to see how you gain information by actually sampling this interferogram, you have the interferogram being built up as we take images and move the mirror. And on the other side, you have the spectrum getting more and more precise. And so you increase your spectral resolution by taking more steps. And in this case, this is a video made by one of my colleagues, Alexandre Vallary, and he was observing a supernova remnant. So if you're studying supernova remnant, you might recognize here H alpha, nitrogen, and sulfur, and you're seeing a perfect characteristic spectrum of a supernova remnant here. So that's how CITEL works. And at the end of the day, you reduce the data cube. So you're not remaining into that interferogram space. You pass into the spectra with the data reduction pipeline, which was developed by Thomas Martin at Laval University. And you get a spectral cube, which you can make a video of and go through the wavelength and see the emission in your galaxy. And of course, you can zoom in into different regions and see a lot of details, actually. So that's what CITEL is, and you can extract spectra from any region of your object. It's a little bit overwhelming at the beginning, but we are developing tools to help you do that efficiently and automatically. And with signals, we have a lot of data, and so we have to build these tools that do the work automatically. We have thousands of objects, millions and almost billions of spectra. And so the development of those tools are essential for the good being of the survey. And of course, it's not only about emission line, but it's also about kinematics. So we develop tools also regarding the kinematics of objects. So CITEL was born from basically the strength of CITEL, because CITEL is the only instrument right now that can cover nearby objects that are super extended on the sky. And also, the fact that they are nearby, you have more resolution on the star-forming regions. And so you can really dig into the physics of those star-forming regions. And about a year after I arrived here at CFHT, I developed this program with my co-PIs that you might recognize here. So you have Pierre Martin, Carmel Robert, Laurent Thyssen, and Philippe Amram. And we suggested a large program with CITEL that was Signal. And Signals is really trying to tackle things that you cannot tackle with any other instruments currently and efficiently. I mean, you could, but it would take forever, literally. So it's a large collaboration. We have about 17 countries involved, about almost 70 people now. And each groups have different expertise that helps the science with signals. So there's so many things that can be studied that we needed a team that was very diverse and in expertise to conduct it. We had a workshop in 2019, so before the pandemic, and we are planning to do another one. And we're actually a very welcoming team. So if it's anywhere related to the science you're doing, feel free to contact me. But yeah, this is a picture of the people that attended to the first workshop. And now to dive in, I don't have a time clock here. I hope I'm not busting my time already. Usually I have my phone by here. So
about 20 minutes left.
20 minutes, perfect. Yeah. So diving a little bit into the science and what has been done with signals so far and some of the topics that we are planning to tackle in the next years to come. So signals observations started in 2018 in the B semester. So like in September of 2018, and it's a 4-year program. And we are observing about 40 galaxies to collect information on a lot of H2 regions, about 50,000. So we are on our last year of observing. We should complete the data acquisition in the semester A of 2022. And so why do we wanted signals? So to study star formation rate, yes, study star formation efficiency, and also tackle the stellar initial mass function of the massive stars. And we wanted to do that in the context of where the H2 regions are, their environment. So we talked a little bit about the ISM, how the ISM have different properties. We talked about the surrounding stellar population and diffuse NS gas that are around that can have different properties as well. And of course, all of this is kind of integrated, and this actually might have an effect on star formation rate, on star formation efficiency, and stellar initial mass function. So this environmental context of the H region is what signal is looking at. So we have sample galaxies that have very various characteristics to sample H2 regions in all of these different locations, a very low density, very high density, both of ISM and stellar population, and level of activity. And this is really the key here, because we want to study what is the effect of the local environment on the star formation process. So you probably know a lot of surveys that are studying galaxies. Like we are surveying 100,000 galaxies at different redshift, and we're studying how their mass is related to their star formation rate, for instance. So they don't necessarily dig into the galaxy on a sub-parsec scale or a sub-kiloparsec scale to understand why it is so. So for H2 region, the fact that they are in a big galaxy or a small galaxy is very not necessarily relevant, in the sense that they live for just a few million years. And what they see around us, what affects them, is their local environment. So digging into this, the signal survey is a survey of H2 region and 40 galaxies. And it's really looking into the local environmental effect and not the group or like galaxy group effect. It's just completely different scales. So the survey stands for Star Formation Ionized Gas and Nebular Abundances Legacy Survey. And I hope by now that you understand why we picked that acronym. And we're looking at those H2 regions, individual H2 region, in very different, like either they are like close to the center of a galaxy, in the outskirt, massive, less massive, extra, like ultra massive region that are very complex, and some that contains O star, some that contains B star. And just by looking at these images, I can tell you a little bit, just because I got used to it, that you have more massive stars in some region. And also very detailed information on the 2D spatial distribution of the emission in the H2 region with this spatial resolution we reach with signal. So we don't go beyond 10 megaparsec. So all of our galaxies are really close by. And the physical scale of the data average on about 20 parsec, but we do have targets that are closer, up to a scale of about 1 parsec, and it goes up to 40 parsec. And a little bit more, because sometimes data image quality can vary at the telescope during the observation. And some of the more detailed aspect of the analysis, we also kind of mix all the information that we gather from the H2 region to study global aspects. So we have teams that are also associated with feedback processes. So we do have a lot of information about the turbulence in the gas, supernova remnant, and a few of our galaxies are active, galactic nuclei galaxy, AGNs, and also with the structures of galaxy and how the interstellar medium actually mix in the galaxy. We have teams that are looking into this. So signals, like how signals is positioned with other surveys that are studying galaxies is really related to the detailed information we get, and the fact that other galactic surveys lose information as they go further, as you actually observe further. So when you observe object in the Milky Way, let me go just here, like the Orion Nebulae, you have a lot of physical information that are actually spatially known in 2D. So you can know the temperature of the electron, their density in 2D. You can also know the amount of dust on your line of sight in 2D. And you can actually know the exact mass of some of the stars in there and their position very well. With signals, you're just the level of information beyond, so you lose a little bit already. You have to do some assumption, including some IMF assumption. So you might wonder how I'm going to deal with these IMF assumption and studying still the IMF, the massive star. And I can talk a little bit more about that. And then if you go beyond that, you really do a lot of assumptions. So you don't have any information about what's going on in detail in the gas. You might use global abundances like cluster mass instead of stellar mass and in a very integrated way. And of course, you always do IMF assumptions. And cosmological surveys with those galaxies that are much further away are just the ultimate assumptions here. So with signals, we hope to be able to provide the community with relationship of the star formation activity with the local environments, so that these assumptions that are used for larger surveys that are going beyond can be more precise and therefore helps us to study star formation activity throughout the age of the universe. And so it is, like, for me, it really is building a tool for astronomers to, get a better estimate of what's going on in their object, no matter where it is, no matter how well they see it. And this is what it looks like in signal. So really, we have really high resolution or up to this level of spatial resolution. Now the data cube that we have are in 3 bands. This is the SN3 bands, but we also have a green and a blue band. And the typical emission line that we get are those here. So O2, O3, H beta. If you study the ISM, you might recognize those. If not, it's okay. And then we also can sample sky spectrum very well and subtract it because we have such a large field of view. And this is a data cube of M30, a section of M33. We have a mosaic of M33 in this survey. And you can see as we go through different lines what it's looking like here. And the amount of information that is in each. So if I zoom in each region here, I can show you some of the dynamic information here just through H alpha, and you can see the different filaments going at different velocity. And this is the crazy slide I had prepared for Casca during the last Casca meeting. So you might have seen it. Hope it's still running on your end. But it's all the galaxies that had been observed prior May of this year. And I had run all the identification procedure on these galaxies, and we had about a little bit more than 30,000 regions, but now it's not true anymore. After the last semester, we are above 40, and we have a very large semester left with a lot of data. So I know I will reach my 50,000 region, which was the goal of Signal by the end of the acquisition. So all of these procedure of identification were run. This is just an example on one galaxy that has a lot of H2 region. And if you zoom in, you have the same output that I showed you earlier with the ionization source and their boundaries. And this is very useful to have a tool that automatically identify them. At this stage, you don't know if it's an H2 region or a planetary nebula or a supernovae. But at least you get the first step into identifying this emission line region. And then once this is kind of done, you can start to dig in and like do a little bit better. So you want to take care of the the diffuse ionized gas. You want to remove it. You want to also study the spatial distribution of the emissions. So we have different models right now. This is like a spherical model. So if you just look at the emission as a function of the distance, you can produce a profile for each region very quickly. But you could also do something a little bit more fancy. We are developing tool for 2D, like elliptical shaped regions. Some of them are very spherical. Fortunately, more than half of them are. Some are very complex, but this is like a way to get very quickly those easier regions to study that have normal, easy morphology to look into. And so for each of them, you can subtract the diffuse ionized gas background using some of the tools that were developed also to kind of estimate the emission of the diffuse background. And you have regions that, like I was saying, that are spherical, like this one here. You have some that are definitely not spherical, and some that are more diffuse and filamentary. And these regions, like you can see in their profile here, so for each image you have their profile, you can see there's a lot more dispersion. So we have automated way to characterize their morphology. And some of them will only have enough signal in H alpha, but not necessarily in the other lines. They're still useful to study like the luminosity function of H2 region, but not necessarily study in detail the abundances. They're still useful for the IMF, but not, you know, there's like each region have their own level of information that they give you. And so we automatically screen into this using these procedure. And as I was saying, we're not using only H alpha for the detection, it's also H beta and O3. And we have very good accuracy in doing that. Like in NGC 628, which was published, is more than 4,000 regions in the galaxy and less than 0.5% of false detection, which is great. It can never be perfect, as you probably know, but this procedure is very good at doing its job. And also you have to account for different things, like also one thing that I like to point out, and I talked a bit about the diffuse ionized gas, but not necessarily the size of the region. So we can measure the size of the region very precisely, including information about the seeing and the distance of the object. And so this is, for the first time, you know, you can integrate all of these parameters together in a catalog of H2 region that you can then use to do a lot of science. So some of the first, you know, analysis produced that you can do with such a catalog is, of course, studying the luminosity function of H2 region. So you have the luminosity as a function of the number of regions that are there. You have here two different curves, which are the observed one and the dust corrected one. You can start playing with other parameters. Give me a second here, I have yeah, so here I had like the same sample, but instead of, I used the dust corrected sample and I split it into as a function of the distance where they are in the galaxy. So the one that are in the center of the galaxy here in red versus the one that are in the outskirts, or the ones that have more or less diffuse ionized gas around them. And you can see difference in different groups. And I mean, with all respect, you can play with this in so many different ways, selecting what you want to look into. And that's the power of such a large catalog. You can then start to study effect just by selecting different groups. And there will still be statistically significant because you have such a large sample and thousands of regions you can pick into. And they are all analyzed in a very systematic, same way. One other thing that is super cool, you know, I talked about morphology, spherical region, diffuse region. And if we zoom in into M33 here, you might have not recognized it. This is M33 emission from the gas. And what I wanted to point out here, you have those very like bubbly looking with the pink surrounding region. And then you have these here that are orange with like very fuzzy contours. And this is a thing that, well, when you study the ISM, you might know why it is so. So you have some regions that are what we call matter bound or ionized bound. And those two definitions are very confusing, but it's basically if you have a region that is surrounded by neutral gas or a region that was able to ionize everything around it, then you have photons that can escape it. And they will have different size than what is predicted by a typical model if you don't have enough neutral gas around it to be ionized. So these regions here have a lot of photons actually escaping, while those here are bounded by neutral gas. And in some cases, you can have a region that is bound on one side and unbound on the other side. And you can think about ways of studying emission in a 2D fashion, like looking at the radius around your H2 region, looking at different lines, and study the density of the medium in the different lines, and you will get different values. But still, studying how many regions are bound versus how many regions are unbound is very relevant. And if you don't do that, if you don't study if they are bound or unbound, a region that is not bound and has a lot of photons that escape can mimic a smaller mass of massive star in the center. So that said, with Signal, we have the tools to go beyond that bias. And this is why we're again getting a little closer onto the initial mass function of the massive star. And this is like, yeah, those typical models here with the ionized bound region with the neutral gas and unbound region here. And so this is just a quick, and I'm probably busting my time here, but yeah, more or less. Okay, I'll just try to go very quickly through a couple of things that are, to me, very interesting. And I hope it will trigger some of your interest. But here is just some comparison with the radius of the region and their luminosity. So if you have, and you use the Stromgren model, you can get different prediction of the luminosity as a function of the radii. And of course, it varies depending on what's the condition in the gas. And so you have these different models here, depending on the electron density and temperature, and also the filling factor. But what I think is pretty cool is you see those regions that are super bright and super small. Those are actually the ones that are attached to the unbound region. So these guys here, they're too luminous for their size. And the photons are escaping and there's nothing that prevents it to happen. They should be bigger. If there was enough neutral gas around them, they would be bigger, but they're not. And so this is just an example of that. And then let me go a little bit further here. So we have photonization models to modelize the emission of the line, also depending on different condition in the gas. So these model can be twisted and used in different ways. It can be a grid of model that you apply on your observation, and you can study one region at a time. So that's one technique. You can also have models that evolve through time that includes a little bit more of the mechanic, the stellar wind, and where this region is at in its evolution stage. So this is an example of 3 regions in the same galaxy. These are the 3 up there that have, fortunately for me, about the same luminosity in H alpha. And you can see, you might recognize them here. So they are in 3 different stages of evolution, where you have this very dense region here. Stellar winds started kicking in, and then you have this shell and expansion at the end. And you can see how they differ in their emission here. So that's one tool. And then you can also use groups of region as a population in combination with the model. You can study them individually, or you can study them spatially in 2D and look at one region at a time and start digging in. And since I'm busting my time, I think you probably are full with information about Signal right now. I'm just going to say that more recently, I just wanted to make some plug here. I've been working with a student at Montreal on machine learning techniques to tackle all of the kind of tool we want to develop for such a survey. And one of the last one is to just quickly identify if an emission line region is a niche region, a planetary nebula, or a supernova remnant automatically using the machine learning methods. So this is coming up. We are actually building on building a larger grid of models for planetary nebula. It was needed to get into our larger model grid of model, but it's coming up soon. And we have these fantastic teams. There's 10 of them that have different kind of responsibilities within the survey. And depending on where we'll be at, some teams will be more active. So hopefully within the next couple of months, you'll see coming out one of the first catalog of H2 regions from Signal. I strongly encourage you to probably dig in and try to do your own science with it. And if you have any questions, or if you have any ideas of a parameter that should be in the catalog and you have a way to extract it, please contact me. I'll be happy to make it work, and run it on the data so that we can have an even larger catalog. And thanks for being here and listening to my presentation today.
Thank you very much, Laurie. Thanks. Thank you very much. Virtual applause all around. That was a wonderful talk. So questions. Give everybody a moment. Oh, David, go ahead.
Hi, Laurie. Great talk. I must admit, gave me cold sweats at the start of it, hearing about hurricanes and thinking about my time just supporting the old FTS on the summit more than 25 years ago. I remember being up at the summit with Jean-Pierre Maillard many nights when it was absolutely miserable out, hurricane force winds and snowing and blizzard. We managed one night to hook the bumper of the truck on the way down the hill over the guardrail near the IFA telescope. I hope the new FTS is more reliable than the old one was. The old one, trying to maintain the laser stability was a huge issue.
Okay. Yeah, no, we are getting to a smooth, it's a smooth ride with CITEL now. The first few years, you always have to adjust things here and there and improve the data, but it's been a good 2 years that we haven't had like major issues. Sometimes you have to change a laser, but so far so good for this one. And yeah,
David, technology has improved since the last century.
Yeah. And I laughed because I found my old manual still available on the Series 2 website. I put a link to it in the chat.
Yeah, I saw that.
All 75 pages of it. Anyways, nice talk. Thanks.
Yeah, my pleasure.
Awesome. I've always been really interested in I'll ask a question. In the diffuse ionized gas itself, I know you mostly talked about subtracting it off, but so what kind of surface brightness limits do you get to roughly? It looked like maybe a little bit below 10 to the negative 17.
The thing is, it depends on what special resolution you need, because if you bin, then deeper. And so we have a team actually very interested in the diffuse ionized gas. I'm in some of the teams that are not, so I do. Sure. But as I said, you can use the level that you measured as a tool to then study different things. And of course, you expect the diffuse ionized gas to be somehow related to the amount of photons that escape the region, but also the condition in density of the gas and temperature of the gas in that specific galaxy or the specific radii of the galaxy.
Absolutely.
So it is part of the catalog, the level, let's say like the H alpha surface brightness of the diffuse ionized gas. But like if you would say, oh, Laurie, is it possible to extract like some line ratios and this, then I can totally make it work, and you will have at least for some of the region enough signals to get some of that information.
Awesome.
So yeah, everything is possible.
No, it's an amazing catalog. Dennis, you had a question. Go ahead.
Yeah, great talk, Laurie. I really enjoyed it. So my question is, I know some of the work Carter's been doing and others with, Sebastian from our place on machine learning. Are there other areas where, that using machine learning techniques are being used to explore CITEL data or signals data? And what do you see as the future for that approach?
Yeah, we've gained a lot of time in, first of all, doing the spectral fits of the data. We had a first approach that was using a catalog of H2 region as a training set, but it's a little bit constraining because so many of the spectra are not necessarily H2 region dominated. And so we are building like a tool that will be more like a CITEL broad tool with Carter that will fit anything basically, but just instead of using the typical minimization techniques for the fittings, you would have literally like the machine learning trained algorithm to do your fits. And the amount of time that we saved is tremendous. It's like up to a level of 100 times faster. And you know how annoying it can be when you start fitting something and you notice that your input are not accurate and you have to fit it again and again and again. And it's an endless game. But if you gain 100 time efficiency on this, then you can think about refitting the whole signals, billions of spectra, within just a few days instead of months. So if ever, we noticed that, we could have added this, or like, and especially when you have multiple velocity components, we have a technique that split spectra that are single component, multiple. And we are just putting these bricks, of codes that are doing different, increasing the efficiency of it. So the machine learning is absolutely essential for a sample like this. We could survive with traditional tools, but it would be painful and very long. Yeah.
Thank you.
So we can, if Laurie is available, we're a little past the hour. We can keep asking questions, but if you have to go, just let me know.
Another meeting. Yeah, I have another meeting. I'm already late.
Okay, then maybe we should wrap it up.
And we were talking about the 0 to 5 minutes late astronomer at the meeting. Yeah, I'll be the late one at the next meeting.
Then in that case, I'll stop recording, and thank you all very much for coming. And thank you very much, Laurie, for a wonderful presentation.